My name is Jae Edmonds, and I work at the Joint Global Change Research Institute, which is a collaboration between the University of Maryland here at College Park and the Pacific Northwest National Laboratory. So my office is across campus in M Square, and I work on the integrated assessment of climate change. Well, certainly from the perspective of someone who works on the integrated assessment of climate change, we see the big challenges as trying to pull together the energy, economic, agriculture, land use, terrestrial carbon, and other biogeophysical systems together with climate change and the policy environment as our big challenge. The talk today is going to look at a new question, which is taking as given a challenge to limit the forcing of climate to 2.6 watts per meter squared, and that level of forcing is often taken to be consistent with limiting climate change to no more than 2 degrees relative to pre-industrial temperature for the average on the planet. Given that as a goal, can you do it without a particular technology combination, which is referred to as bioenergy with CO2 capture and storage? And the background is that to date, any number of studies have been able to demonstrate that it can be done with bioenergy and CCS, but nobody has asked the question, if you didn't have it, could it still be possible? So I'm going to investigate that today. And the short answer to the question is yes, it's possible, but it's more expensive, and it gets harder the less perfect the policy environment is. Well, it's exciting because it bears directly on critical policy questions that are on the table today. It looks at this question of feasibility. Are the goals that the science and policy communities have been setting, which have over time become increasingly ambitious, while at the same time the policy interventions that have been engaged continue to be modest? Are these goals still even worth talking about or not? And the research that we're undertaking really try to answer that question, but also get specific about, given the way that the human and earth systems work, what actually has to be done and when does it have to be done, and which systems need to be engaged to reach these goals. Some of the key findings are that, in fact, it is feasible to achieve these low stabilization targets, even if you don't have bioenergy and CO2 capture and storage. It's much more expensive as you drop out the technology options from the mix, such as either bioenergy or CO2 capture and storage or nuclear energy, and that the cost penalty interacts non-linearly with the policy environment. And so as policy environments become less efficient, then costs rise, and costs rise non-linearly with the interaction between that and technology availability. That we reaffirm this basic finding that eventually all of the major regions of the world have to be engaged. These low stabilization goals are achievable even with delayed participation if before the end of the century all of the major regions are part of the mitigation regime. But if you leave out important regions of the world that never engage, then it becomes impossible, for us at least, with our modeling tools to demonstrate feasibility, even if you have the full technology set available. In addition, we find that while much of the attention in the research community is focused on CO2 capture and storage to allow fossil fuels to continue to be used without increasing the concentration of greenhouse gases in the atmosphere, we find that terrestrial sequestration is potentially extremely important and can, if policy tools can be mobilized to motivate storage of carbon in terrestrial systems, that is in forests and soils, that this is a potentially very large and important opportunity for mitigating emissions. Finally, we find that the geologic formations from which you could store CO2 don't present any meaningful constraint on the deployment of either bioenergy or CO2 capture and with storage in geologic repositories. And land is not a meaningful constraint as long as the policy environment can be made to mobilize those resources. Well, the policy implications are, I guess, a couple of things. One is that technology suites are really important, and that you can give up technologies. That is, you can say we're not going to utilize them, but they have cost consequences. It also says that it's not too late to achieve some of these ambitious goals, but that in achieving them using policy instruments that are economically efficient pay big dividends, and particularly in the more realistic world where it's likely that some parts of the world won't be able to engage in meaningful emissions mitigation for extended periods of time. In that setting, it's increasingly important to have a full suite of technologies available if costs are to be controlled. So I think there's some good news, but also some hard news that come out of this research. Well, certainly there's a lot of questions that are left unanswered by this research. Certainly the modeling tools need to be improved. A couple of directions that we are working very, very hard to improve are our representations of terrestrial systems and the engagement of realistic policies to try to understand what is it that could be achieved in policy environments that are likely to be deployed. And then finally, improving our representation of hydrologic systems in the Earth system, and how do they interact with the human Earth systems. So there's a lot of work that's left to be done, and we're going to be finding new results for a long time into the future.